Hello, Poe. I'm Professor K. This is Time Travel and the Twin Paradox. I'll start with the twin paradox. What is it, right? So if you have a pair of twins, I'll just draw my twin here. Pair of twins. Okay? And one takes off in a rocket going really fast. Okay? And when he returns, he's now younger than his twin. His twin has aged, and hasn't aged as much. And why does this happen, right? The paradox is suggesting that, if this guy's moving away from him, why would it matter if he was moving away from him or if he was moving away from him? Why does it matter which one's moving? The reality, and I'll jump right to it, is that intuitively it seems like it shouldn't matter which one's moving. But the reality is that it does matter which one's moving. Okay? And that's why it's not really a paradox, and I'll explain why. For all intensive purposes, if you had these two twins floating free in space, okay, and as far as either one of them could tell, they don't know which one is moving, okay? So if this is, twin A here and twin B, and what twin B sees is he sees A go floating by. As far as he's concerned, he's sitting still and twin A is the one going by. But from twin A's perspective, what he sees is twin B go floating by. As far as he's concerned, he's sitting still and he's going by. It's kind of like, if I hold this, I'm going to try this. If I hold this marker still and I move across, as I move, it looks like the marker, from my perspective, is moving, okay? Versus going like this. Why does it matter which one, right? So what's going on here is the reason the twin that's moving ages less has to do with something called time dilation due to our space-time, or the continuum or ether, the stuff that we think of as nothing, that permeates the entire universe. It does care about motion. I know care is kind of an odd word to use, but it seems that built into this fabric of the universe is this effective motion in it, and it's referred to as time dilation. And so now I want to show an example of how this works with this pair of twins, and then I'll come back and explain the how and the why. I'll circle back around. But first we're just going to jump right into, we're going to try to give this some sense of reality of if you could do this situation. So we're going to try to make it somewhat as plausible as we can. So we're going to start with two rocket ships, okay? And I'm going to have them both, twin A and twin B, take off in their rockets. For further explanation later, you'll see why. Okay? So, and we're going to have these twins. They're going to leave from Earth here. We'll draw Earth. And they will be twins A and B are 20 years old, and they'll leave Earth in 2020. Okay? So in 2020, A and B are twins on Earth. Okay? And they're both 20 years old. Now we're going to set them going at about 99.5% the speed of light. Now, we can't quite get anything that has matter to go the speed of light, but we can get pretty close. And for this sake, we're going to try to get really, really close, 99.5%. Now, in order to do that, you're probably going to have to build some giant accelerator, out in space, or around Mars or something, and you're going to have to end up with some tail of it, that's linear, because at some point you're going to have linear acceleration, and these guys are probably going to have to come shooting out of these accelerators. And to set all this up, this infrastructure of having accelerators out in space, you would probably do it all first with some type of drones or some type of robotics that you've sent out to build, this type of thing. But okay, so they're gonna take off 2020, and let's say when they leave we'll say when them getting up to speed and getting up to this 99.5% C, we'll call this maneuver X. We'll call that the launch. Okay. And that will take 6 months to do. Okay? They have to go in this accelerator, speed up to 99.5% C, and then they leave. And they leave here, it's 2020, 6 months later, they're at the speed of light and they're flying through space. Well, after a year of flying, I'm going to write 1 year. Okay. Twin B is like, I'm tired of flying through space. It's been an entire year in space. I'm going to head home. I'm going to go back to Earth. So he comes back to Earth. And we'll draw his rocket coming back. Here's Twin B returns to Earth. Okay? So it takes him 6 months to get up to 99.5% C. He travels for 1 year at 99.5% C and then turns around. And we'll say this whole turnaround maneuver takes a year because he's got to slow down, turn around, speed back up. So we'll call this maneuver Y. And we'll call this 1 Earth year. Okay? 1 regular year as far as we know. Okay? This 1 year is 1 year of him flying. Okay? And he comes back and he has to do the whole slowing down maneuver as he gets to Earth and lands. And we'll call that maneuver Z. And that'll take 6 months here as well. Okay? So his time spent is 6 months to get up to this. 1 year, he turns around. That takes a year to turn around and come back, and takes another year back, and then it's 6 months. So for him, he's experienced 6 months, 1 year, 2 years, and then this trip back is also a year, right? So 6 months plus 1 year plus 1 year plus 1 year plus 6 months when he returns. That's what Twin B will experience. So it'll be 20 well, let's just say it'll be 4 years for him, right? 6 months and 6 months is 1 year, 2 years, 3 years for this maneuver, and then a year back. So twin B is now 24 years old. Okay? But he doesn't arrive in 2020 on Earth. When he arrives, it actually took him close to 10 years to get out this far as the people on Earth were concerned. So when he returns to Earth, it will be 6 months plus 6 months plus a year. So that's 2 years plus 10 and 10. So it'll be 22 years. So he will have aged 4 years in 22 years by going this speed. Okay? Now, twin A, he says, well, I'm going to keep going. And he goes out for a little bit longer. He hangs out, he's just flying through space, and for him, this is 4 years goes by. And he turns around and comes back. And when he comes back, he does all the same maneuvers. So took him 6 months to get up to this speed. He coasted at this speed for 4 years. It took 1 year to slow down, turn around, and start heading back. And it took him another 4 years to drift back, and then another 6 months to slow down and stop at Earth. Okay? And so twin A, he experiences 6 months here and 6 months here. That's 1 year. This maneuver Y of slowing down, turning around, that's another year. That's 2 years. But for him, he had 4 years traveling this way and 4 years traveling back. So that's 8 years and then 9, 10 years. So twin A is now 30 years old. Okay? But because he's traveling at this speed again, for every year he's traveling at that speed, 10 years goes by on Earth. So for him, this is actually 40 years, another 40 years. He's not experiencing that time. He's only experiencing 4 years. But on Earth, 40 years will go by, another 40 years will go by, and then another year and another year here. So on Earth, 6 months plus 6 months is 1 year, plus 1 year maneuver, plus 80 years, 82 years in the future. So twin A only aged 10 years in 82 years. But when twin A arrives in 2102, twin B was 24 years old in 2042. So for him, 60 more years have passed. So twin B is now 84 years old in 2102. Whereas twin A is only 30 years old. And that makes twin A $54 years younger. Than twin B. Okay? Or you can say, twin B is 54 years older. Okay? Now, like I said, to get going this fast, there'd be a lot of stuff that would have to go into getting people going that fast. And for each year that they experience here, this is 1 year to him will be roughly, or I'm going to say approximately, 10 light years in distance. That's the distance. Okay? So that's 10, 20, 30, he'll go out close to 40 light years. And it from Earth, what they will experience is if they see him, if he's got a little light on his ship, they'll see him take a long time to do it. But for him, it will be relatively short compared to what's happening here on Earth. Okay? And that's how it would work. Okay? At this speed. And you might question, why does that work? One thing I want to point out at this moment, this time dilation or time travel effect of our twins here. What I want to, the reason I drew it out this way is I want to point out it doesn't really have much to do with acceleration. If they both want to get going at a certain speed, they need to accelerate, but they both have the same accelerations. This maneuver X, it's one acceleration to get going this speed. And this guy just sat at that speed for 3 years longer than this guy. They both had the same acceleration here where they slowed down and turned around. It both took them 1 year to do of Earth time. And they both had the same deceleration here when they came back to Earth, and it took them 6 months here. So it's really, what I'm really trying to show is the reason there's this difference in age, it's the time spent at the velocity, okay? I'm going to explain all this and come back to this. But they both made the same accelerations, same exact maneuvers, same exact acceleration, and they just end up with a difference of time, okay? To have a difference in time, you can look at it as acceleration. If you're living on a planet that's, say, orbiting really close to a black hole, you already have this acceleration. So all the people on that planet are going to be experiencing this slowing of time in a sense. They're not going to notice it, but they'll see the universe age more quickly than how we would see the universe age. And for them, they would basically age quicker because if they left their orbit and slowed down, that would be their only acceleration option, is to actually decelerate, not accelerate, and to have a time difference. And once they have that time difference to come back, they would have to speed back up to get back to their planet. But they would just be aging more. It would be the reverse, where they're by going out in space and traveling in their rocket, if their only option is to slow down, then they're going to be the older one, not the younger one. They're going to be the twin B here, to the rest of the people on Earth who will be like twin A, who lives, who's only 30 years old in 2102. Okay. So hopefully you get a good picture of this, because I'm going to show you a little bit of kind of the how and the why this works, okay? So, thanks to, I guess, Albert Einstein for this, we have this wonderful time dilation formula. And what I'm going to do is just kind of show you why this works, why 1 year for somebody traveling at this speed is 10 years compared to somebody on Earth. So our time dilation is, I'm going to write TV equals TS. I'm sorry. So what this is saying here is your t equals time, right? V is your velocity or speed. S is, we're going to say that's the person who's still or stationary, who isn't moving, okay? And then C is the speed of light. Okay. And so if you do this, you'll see that at 99.5%. Now, we don't know what the speed actually is, but essentially what you're doing here is figuring out that percent. So you're taking your speed of light dividing by 99.5, or this other unknown speed, and you're ending up with this 99.5. So if we square that, we get, 1 minus 0.99, which gives us 0.01. And the square root of that equals 0.1. And so your TV is your TS times 0.1, right? So your time at velocity equals the time on Earth times 0.1. So, 10 years goes by on Earth times 0.1. So 10 times 0.1 times 0.1 equals 1 year. So TV equals 1. So your twin is only going to experience 1 year at this speed for every 10 years on Earth. Okay? I don't really like to do all this on here, but I'm just trying to show you, how this time dilation essentially works. The faster you go, the more time slows down. To go from, say, 1 year at a certain speed to equal 2 years on Earth, it's something like 86 or 87%, somewhere around there. At 50% light speed, you're not going to notice much of a difference. You have to get going pretty fast. Okay. And so, why does this work? That's kind of the thing. Why is traveling at these high speeds, slow down your clock? Or why does it, you don't notice time slowing down? And I'll show why. So a lot of it really kind of comes down to geometry and the math behind it, right? But we're going to show our car here. We're going to imagine you're in a car. Driving down the road. Here's you, okay? And you're going really fast in your car. And the thing is when you start approaching these high speeds, your motion forward becomes kind of limited. And so what I'm going to show is why something moving by having another movement. Let's put it this way, okay? So why this guy in his rocket ship ages less? If you think about it in terms of if you're traveling really, really fast here, and you're inside your car, and you're holding a tennis ball, and you just throw your tennis ball up like that, okay? Well, your tennis ball, the trajectory your tennis ball will have now, because it's moving right with you in your car, your tennis ball is going to have a different trajectory. So you traveled this way, but your tennis ball traveled this way. Okay? Let's show a different line here. Let's show the tennis ball in green if we can. Okay? Here's the path of view is, you know, you're both in the car, but the tennis ball has a longer distance to go, and it's doing it in the same time that you're doing it. For you, you know, this up and down motion might be like 1 second, like 1, right? And say it takes you a second to go this distance. Well, that tennis ball, technically, the shortest distance is a straight line, and once you see that it has a different path, then the tennis ball has to be going faster than you. So by you putting energy into that system, into that tennis ball, you've made it not just go the distance you're going, but a little bit more by giving it this trajectory through space and time, okay? And that trajectory that the tennis ball has, because it's a greater distance, it's technically going faster. Again, like I say, this kind of comes down to geometry. Well, at some point, you approach speeds that things cannot go faster. The space and time kind of limit how fast something can really move. And so all these other motions kind of get this, I'm going to say lag effect or drag effect, if you will. So if you look at it in terms of kind of like you're made up of all these particles, atoms and whatnot, and if you look at it like you know, an atom as being a proton and an electron, and I drew the electron way bigger than the proton, but you get my point. Okay, let's try that again. And if you think about it in terms of all these things have like their own little motions to them. They're kind of vibrating and moving in their own little way. And you put some energy into them where they're moving at this really, really high speed. It's like the protons say, let's say this is our nucleus of our atom. And it goes so far, so fast. This electron has a different motion here. So if the electron, say, is trying to orbit this proton, and let's say it's here initially, and the proton's going this way, this electron has to go around that proton and catch up if this is the direction it's going. Now, electrons don't necessarily orbit, but what I'm suggesting here is that whatever secondary motion they have, it's getting extra work done. There's some extra energy, and it cannot really keep up. So when you put a ton of energy into a system, the rest of the components of that system kind of slow down because they're forever in drag. They're trying to keep up. They're getting dragged behind. You know, everything is getting like this, like I say, drag effect to it. Okay? That's one way to look at it. You know, it doesn't have to be necessarily like this is getting dragged along and it can't keep up. But if you think about it, if the electron comes around to this side and the proton is going at 99.5% C, the electron is going to have to be able to come back and continue, say, its orbit. It's going to have to take a longer time. And so if you say, another way to say this is to say that each time it does do its thing, whatever it is, it might not be orbiting, but it might just have a certain fluctuation or vibration to it. If it moves forward and back a little bit, you can say that each moment, let's just say, one orbit equals 1 tick of your clock or 1 second. Okay? And so since it's taking longer for that one orbit, it's going to experience time in a sense because it knows time only as a motion. Time itself is really just our conceptual way of dealing or understanding and handling motions. And that's what it's all based on. So if all the particles in your body are getting slowed down, even your very thoughts get slowed down with it. Every aspect of everything that is you is getting kind of stretched out and this like I say this effect because you're adding all these motions, these quantum motions that the synapses in your brain, how you think is affected by this. Okay, hopefully you get what that means. So you could say in relation to your human, it could be like 1 heartbeat. Okay, so if each heartbeat your heart tries to pump, the backward motion. So if your heart goes this way, the front of it, let's say that this is the back of your heart and this is the front of your heart as you're traveling. As your heart beats, it does this, right? So the front of your heart, when you're going this fast, has got to somehow go faster. But how's it supposed to go faster than what you're already going when you're approaching a speed like this? So it can't. So it gets slowed down. It can't quite go as fast. And then the same thing with the back of your heart. Say it can go backward pretty easily, but now coming back when it comes together, as your heart beats, both the front and the back are moving backward and forward. So every motion, you can kind of look at it that way. Every other motion that makes matter, gives something mass. All these other, little motions get slowed down because of just, really, it's kind of simple geometry. Like I say, I shouldn't say simple, but you see what I'm getting at. And another effect of time dilation is gravity. And there's a formula for that. The point is that when you get near something of a lot of gravity, like on Earth, if you were far away from all other planets and way far outside our solar system, where you weren't feeling the effects of gravity, you might experience time. Well, I shouldn't say you would. To you, the experience of time is always the same, no matter where you are or how fast you're going. I should say that time for you in relation to people on Earth will be moving a little bit quicker because people on Earth, time is slowed down slightly due to the effect of the gravity on Earth. And again, this is not something you would really notice. It's fraction of a second. It's very, very minute, because in order to get these drastic differences of one time to another, you have to get near these relativistic speeds, they're called. Okay. And one of the things that I like to think as to why this is happening, it's not just geometry. I like to think of it in terms of maybe our space-time has some sort of energy to it, or ether, if you will, or particulate, in a way that as you get that as you see gravity as this force, I like to think of it as kind of like a current in a term. Now this is not the way time travel works. This is just my own little process of saying that I think that perhaps if there's an ether, you create this this flow where gravity would be kind of like this current, where if you are orbiting close to a black hole, here. I'll try to draw a black hole. Why, if you're in this planet orbiting close to this black hole, why it's very similar to going in this rocket ship, you know, at a really, really fast speed. Because the stuff that permeates the fabric of our universe, that permeates, to me it would be the same as you going through that is the same as it going through you. It's kind of like gravity, or this ether only travels at the speed of light, and so more massive objects require more of this space-time dynamic nature to converge. And so the space-time itself is in a sense flowing through you. Whereas traveling at a high speed through empty space, not near something of high gravity, is the same effect. To me, that's the way I kind of see it. Whether that's the case, I we don't know, but I'm just saying most of what we do know mathematically is it just seems that it has a lot to do with geometry. It just seems to work out this way, that there's this warpage to space and time. And when you travel at these high speeds, you start to kind of warp a little bit yourself, if you will. Again, I don't know if that's the best term to explain that, but so yeah, I mean, there's other ways, I guess, if you wanted to time travel. So the twin paradox, it's not really a paradox, because it matters to the space-time. Now, the real reason as to why space-time seems to care about who's moving, again, that's kind of unknown. That's why I kind of threw in that, well, maybe there's something to space-time. Maybe space-time is made up of something, and that's something that is what's causing the effect, okay? But it's not a paradox, because the person who is moving is the one that space-time cares about, is going to alter, okay? And the whole reason it was thought to be a paradox was because it was thought like, well, why should it matter, right? But other ways you can time travel is not just by traveling at high speeds. It would be, simply, kind of like cryogenically freezing yourself or something like that. It's the same kind of idea. You're kind of like slowing down time for you in a way. You might not experience it. To you, time might even, seem to be moving normal or even faster. Who knows? But for the most part, your heart is like beating slower compared to everybody else's. Your emotions are moving slower, and that would put you into the future, right? So your clock's slowing down. Can't spell today. Slowing down. You going to the future, okay? Now, people will tell you can't travel into the past. Again, this has to do with our understanding and our logic behind things. We like to think that there is this thing called time, and because of it, we like to think that there was a before or what have you. And really, it just has to do with emotions. But we like to think that you could go back in time. There's not really a known way to do that, but you could, I guess, try to figure out a way to speed up your clock, to go backwards. And I'll explain that in a minute. But if some people say, well, what if you were to travel faster than the speed of light, right? What if you were to go faster? Would you go back through time then? Would time stop and start to like reverse or something? Well, I compare that to like going faster than the speed of light. First of all, you can't do it, but even if you could, it would be like reaching the freezing point of water. once you reach that point where you're frozen still, making something colder isn't going to necessarily just make it unthaw and go the other way. You're just more frozen. You just, time would stop for you once you reach the speed of light. You know, at the speed of light, time would stop. But going faster, it doesn't reverse time or anything like that. So it's just slowing down time for you, so that way everybody else is going a little bit faster. Again, this is never anything you experience. It's only the comparison between you and this, somebody who's experienced time differently. Now, what I talked about here was, okay, well, what if you could speed up your clock and go to the past? Again, now this is something I don't know that you'd want to do, because by speeding up your clock, you'd have to somehow take all those particles in your body again, right? If this is our electron and our proton, for example, and you said, one orbit equals, 1 second of your clock equals one heartbeat. Okay, well, if you want it to equal 2 heartbeats, you'd have to, right? You'd have to speed this up. And to do that, you'd have to somehow put energy into that system somehow and make things go faster. At some point, are you going to be going 100 times faster? I mean, if your heart beats, 60 times, what is it, a minute? Do you really want it beating 600 beats in a minute? I mean, if all the processes in your body were doing whatever, I mean, I guess you would, if every atom in your body was somehow, its quantum state was somehow able to be sped up. Again, I don't know how you would do this, because some of these are already moving, relatively fast with whatever they're doing. They're the gluons binding the quarks are likely moving, around at the speed of light already. So, but anyway, if you could somehow speed this up, the system, then to you would age more quickly, and as you're aging more quickly, everyone else will look like they're slowing down, that they're moving really slow, to you. Okay. I don't know that you'd want to do that, but at some point you think, well, maybe you can put so much energy that you're in a sense aging so quickly that everyone else is like stopped and now they're moving backwards. It doesn't really work that way, because even the light that you take in has a limit, right? So what you're looking at, the light from this marker that I'm looking at, it's taking some amount of time, X, and it's traveling through this space to get to me. I can't reverse those actual photons that are doing that. It doesn't really work that way. You know what I'm saying? So we like to think of some of the stuff that we've come up with, like time, as being able to go in reverse, but it doesn't. It's not really. Most processes are based on motions, and the way we talk about them, it leads us to think that, oh, maybe this can be rewound, or we can, do this backwards. It doesn't. It's one of those things that we like to think that that's possible, but it's unfortunately just not one. That's just not the case. Another way you could possibly time travel. It was theorized with black holes. If you had, say, and it might be a little bit more along the lines of like teleportation or something, right? But if you had say some black hole that was, I don't know, microscopic, and could tolerate that somehow your mass going through somehow then would collapse it or whatever, and you had a paired black hole that was connected via a wormhole, right? And you would come out of this black hole somehow, right? That would be the idea behind wormhole travel. And then this passage connecting these two black holes is essentially somewhere outside of our space-time, right? That's some hyperdimensional, you're in like the 6th dimension or 7th dimension or something. By getting from this black hole to this black hole, you're somewhere outside of our known reality. You've been, spaghettified into a singularity here, and somehow, reassembled here. This is, a lot of theory and conjecture as well. But the only thing that we really know for time travel is the difference that you experience by moving at relativistic speeds, somewhere near or approach the speed of light. Okay. So that's your time travel and your twin paradox. Okay, so you can see it's not a paradox, and time travel, how I talked about the atoms in your body, kind of like, trying to keep up in a sense. Okay. I don't know that you would ever want to travel. If you could go in reverse where you'd age more quickly, I don't know why you'd want to do that, to be honest. To speed up your clock, because if you wanted to go age 10 times quicker than you currently are while everybody else stays young, it's like, well, even if you could, I don't know that you'd really want to, but who knows? Okay. So that's it. I hope that helped. Again, these videos are, just to help give a perspective, my little take on some of this. Thank you. I'm Professor K.